Hello everyone, and welcome to today's lecture video, which is on the zeta function and the very closely related eta function. And today what we're going to do is derive a formula relating the zeta function, which is namely zeta of s equals 1 over 1 to the s plus 1 over 2 to the s plus 1 over 3 to the s plus ... where s is a complex number, to the eta function, which is the following: eta of s equals 1 over 1 to the s minus 1 over 2 to the s plus 1 over 3 to the s minus 1 over 4 to the s plus ... minus ... So the eta function is like the alternating version of the zeta function. And then once we've derived that relationship between the zeta function and the eta function, because we already know the value of the zeta function on the positive even integers, we can use that relationship to then find values for the eta function. So for example, we can find eta of 2, which is defined to be 1 over 1 squared minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared ... In fact, we'll be able to derive a general formula for the eta function on the even integers, just like we did for the zeta function. And then lastly, we'll show how the eta function gives an analytic continuation of the zeta function from its original domain of definition, which is the complex numbers with real part greater than 1, to the entire right complex half plane. So in other words, complex numbers with real part greater than 0. So let's start by deriving this relationship between the zeta function and the eta function. So please recall, zeta of s is defined to equal 1 over 1 to the s plus 1 over 2 to the s plus 1 over 3 to the s and so on. And now the first thing that we're going to do here is divide both sides of this equation by 2 to the s. So then I get zeta of s over 2 to the s equals 1 over 2 to the s times the original zeta function, which is 1 over 1 to the s plus 1 over 2 to the s plus 1 over 3 to the s and so on. So then when I distribute, I get zeta of s over 2 to the s equals 1 over 2 to the s times 1 to the s plus 1 over 2 to the s times 2 to the s plus 1 over 2 to the s times 3 to the s and so on. So then when we combine terms in the denominators, we get zeta of s over 2 to the s equals 1 over open parenthesis 2 times 1 close parenthesis all to the s plus 1 over open parenthesis 2 times 2 close parenthesis to the s plus 1 over open parenthesis 2 times 3 close parenthesis to the s and so on. So what do we end up with? We end up with zeta of s over 2 to the s equals, doing these multiplications in the denominator, 1 over 2 to the s plus 1 over 4 to the s plus 1 over 6 to the s plus 1 over 8 to the s and so on. So I'll just move that result to the second line here. And now what I want to do is multiply both sides of zeta of s over 2 to the s, and what that equals, I want to multiply both sides of this equation by 2. Okay, so then when I do that, I have 2 times zeta of s over 2 to the s equals 2 times this infinite series. So it's 2 times open parenthesis 1 over 2 to the s plus 1 over 4 to the s plus 1 over 6 to the s plus 1 over 8 to the s plus ... close parenthesis. So then when I distribute, I get 2 times zeta of s over 2 to the s equals 2 over 2 to the s plus 2 over 4 to the s plus 2 over 6 to the s plus 2 over 8 to the s and so on. So I'll move that equation to the second line on the screen here. And now comes the key step. We want to produce the eta function. Well, how can we do that? We can do that by subtracting the second equation here from the equation up top. So when we perform that subtraction, we get zeta of s minus 2 times zeta of s over 2 to the s equals, now this is really cool, look what happens. We have 1 over 1 to the s, but then we have plus 1 over 2 to the s minus 2 over 2 to the s. So that gives us 1 over 1 to the s minus 1 over 2 to the s. And then the 1 over 3 to the s term is left alone, so we have plus 1 over 3 to the s. And again, we have plus 1 over 4 to the s minus 2 over 4 to the s. So that gives us minus 1 over 4 to the s. And then the 1 over 5 to the s term is left alone. In other words, all the odd denominator terms are left alone. Denominators that have an odd number raised to the power of s, while all the even denominators raised to a power of s, those all become negative because of this subtraction. So in other words, zeta of s minus 2 times zeta of s over 2 to the s, what does it equal? It just equals eta of s. So now I just want to simplify this expression a little bit, and I do that by factoring out the zeta of s from the left-hand side. So I get zeta of s times, open parenthesis, 1 minus 2 over 2 to the s, close parenthesis, equals eta of s. Now on the left-hand side of that equation, I have a 2 in the numerator and the denominator, so I can just write it as zeta of s times, open parenthesis, 1 minus 2 to the 1 minus s, close parenthesis, equals eta of s. And that's the most succinct form of this result, so I'll just put a box around it. And now what's so great about this formula is that we can use it to very quickly derive values for eta of s, since we already know so much about the values of zeta of s. For example, we already know that zeta of 2, which is 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus ... equals pi squared over 6, right? That's the result that catapulted Leonhard Euler to fame. Okay, then we know that eta of 2, which is 1 over 1 squared minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared plus ... minus ... we know that that will equal zeta of 2 times, open parenthesis, 1 minus 2 to the 1 minus 2, close parenthesis. So now subbing in pi squared over 6 for zeta of 2, we have that this equals pi squared over 6 times, open parenthesis, 1 minus 2 to the negative 1, close parenthesis, which is just pi squared over 6 times 1 minus 1 half, or pi squared over 6 times a half. And so we find eta of 2 equals pi squared over 12. Let's do a couple more examples. We found that zeta of 4 equals pi to the 4th over 90. Therefore, we have that eta of 4 equals zeta of 4 times 1 minus 2 to the power of 1 minus 4, or 1 minus 2 to the negative 3, which is pi to the 4th over 90 times 1 minus 1/8, or pi to the 4th over 90 times 7/8, which equals 7 times pi to the 4th over 720. All right, here's one last example. We know that zeta of 6 equals pi to the 6th over 945. So then we can derive that eta of 6 equals pi to the 6th over 945 times 1 minus 2 to the 1 minus 6, or 1 minus 2 to the negative 5. Well, 2 to the negative 5 is 1 over 32. So we get that eta of 6 equals pi to the 6th over 945 times 31 over 32. And I'll leave off the computation there. So based on this formula connecting the eta function with the zeta function, we can derive a general formula for the eta function on the positive even integers. And I'll just ask you to recall that in general, zeta of 2n, where 2n is a positive even integer, equals negative 1 to the n minus 1 times b sub 2n, that's the 2nth Bernoulli number, times 2 to the power of 2n minus 1 times pi to the power of 2n, all over, open parenthesis, 2n, close parenthesis, factorial. And again, this is the definition of the zeta function for positive even integers. And you can see my earlier video where I derived this important formula. And again, this amazing formula connects the values of the zeta function on the positive even integers to the all-important Bernoulli numbers. So now I'm going to use this formula for zeta of 2n by multiplying it by the factor 1 minus 2 to the 1 minus 2n to derive a formula for eta of 2n. So I've written that on the top line there. Eta of 2n equals 1 minus 2 to the 1 minus 2n times my formula for zeta of 2n, which I have there. So then when I do this multiplication, I get eta of 2n equals, well, first 1 times this product, so negative 1 to the n minus 1 times b sub 2n times 2 to the 2n minus 1 times pi to the 2n all over 2n factorial, and then minus 2 to the 1 minus 2n times this product again, times negative 1 to the n minus 1 times b sub 2n times 2 to the 2n minus 1 times pi to the 2n all over 2n factorial. And now in the second term there, something very cool happens. The 2 to the 1 minus 2n cancels the 2 to the 2n minus 1, because when we add those exponents, they of course add up to 0. And so now I'll just factor out the negative 1 to the n minus 1 from both of these terms, and I get eta of 2n equals negative 1 to the n minus 1 times the quantity b sub 2n times 2 to the 2n minus 1 times pi to the 2n minus b sub 2n times pi to the 2n, all over 2n factorial. And now we're almost done. I'm going to factor out a b sub 2n times pi to the 2n from both of these terms, and I get eta of 2n equals negative 1 to the n minus 1 times the quantity b sub 2n times pi to the 2n times the quantity 2 to the 2n minus 1 minus 1, all over 2n factorial. So let me put a box around that, our beautiful formula for the eta function on the positive even integers. And now finally, I'd like to show how the eta function eta of s, where s is a complex number, gives us an analytic continuation of the zeta function to the set of all complex numbers with real part greater than 0. Well, to do that, I want to start by establishing the following claim, which is that the zeta function, as it was originally defined, zeta of s equals 1 over 1 to the s, plus 1 over 2 to the s, plus 1 over 3 to the s, plus dot dot dot, where s is of course a complex number, converges for all s such that the real part of s is greater than 1. Now, why is that the case? Well, consider, if I have some number, some positive integer n to the s, that equals n to the a plus bi, where a is the real part of s and b is the imaginary part, and that will then equal n to the a times n to the b times I, and then by the laws of exponents that will equal n to the a times e to the ib log n, and then making use of Euler's identity, this will equal n to the a times the quantity cosine b log n plus I sine b log n. Well, now let's consider the magnitude or modulus of n to the s. The modulus of n to the s would be the modulus of this expression n to the a times, open parenthesis, cosine b log n plus I times the sine of b log n, close parenthesis. But we know from the arithmetic of complex numbers that the modulus of a product of terms is equal to the product of the moduli of the individual terms. So this will equal the modulus of n to the a times the modulus of cosine b log n plus I sine b log n. And since n and a are both real positive numbers, the modulus of n to the a is just n to the a. And then the modulus of the second term here would be the square root of cosine squared b log n plus sine squared b log n. But if b log n is just our theta, cosine squared theta plus sine squared theta always just equals 1. So we end up having that the modulus of n to the s just equals n to the a. That is to say that the size or the modulus of n to the s depends completely on the real part of s, and the imaginary part of s makes no contribution to the ultimate magnitude or modulus of n to the s. So then, when we want to consider the convergence behavior of the zeta function, we can look at the modulus of the zeta function. So the modulus of the zeta function is just going to be equal to the modulus of 1 over 1 to the s, plus 1 over 2 to the s, plus 1 over 3 to the s, plus 1 over 4 to the s, and so on. But then we know by the triangle inequality that the modulus of zeta of s must be less than or equal to the sum of the moduli of the individual terms in this series. So in other words, the modulus of zeta of s must be less than or equal to the modulus of 1 over 1 to the s, plus the modulus of 1 over 2 to the s, plus the modulus of 1 over 3 to the s, and so on. But we already showed that for n being a positive integer, the modulus of n to the s is just n to the a, where a again is the real part of s. So these moduli are just equal to 1 over 1 to the a, plus 1 over 2 to the a, plus 1 over 3 to the a, and so on. And this series, 1 over n to the a, where a is a real number, this series only converges where a is greater than 1 by the integral test. So this argument demonstrates that zeta of s converges for all s such that the real part of s is greater than 1. So if I wanted to represent graphically the set of values over which the zeta function, as we've defined it thus far, is known to converge, we can draw a complex plane. and I can shade in all the values to the right of the dashed line representing complex numbers whose real part equals positive 1. So I've shaded in purple the set of values where the zeta function converges. This is all complex numbers s such that the real part of s is greater than 1. But now let's compare the domain of convergence of the zeta function to the domain of convergence of the eta function, which again is defined as eta of s equals 1 over 1 to the s minus 1 over 2 to the s plus 1 over 3 to the s minus 1 over 4 to the s, and so on. Well, as we saw before, we know that the modulus of 1 over n to the s just equals 1 over n to the a, where a is the real part of s. But then because we know that the modulus of 1 over n to the s tends to 0 as n tends to infinity for all s whose real part a is positive or greater than 0, then by the alternating series test, we know that eta of s must converge for all s whose real part is greater than 0. Graphically, that means that the domain of convergence of the eta function is the entire right half plane, the set of all complex numbers whose real part is greater than 0. And now here comes the analytic continuation of the zeta function. Because we already know that eta of s equals the quantity 1 minus 2 to the 1 minus s times zeta of s, we can rearrange this formula to write zeta of s equals eta of s over 1 minus 2 to the 1 minus s. And now why is this new definition of the zeta function interesting and useful? Well, we've already seen that eta of s converges for all s with real part of s greater than 0, and the expression in the denominator 1 minus 2 to the 1 minus s, that's an expression that's well defined for all s, including s with real part greater than 0. And we might also note something interesting here, which is that when s is equal to exactly 1, the real number 1 with no imaginary part, we get 0 in the denominator, which suggests that we have a pole for the zeta function at s equals 1, which is in fact true. I haven't mentioned that fact so far, but it is nice to see that that comes out of this definition as well. But really the main point to be grasped here is that by defining zeta of s in terms of eta of s, we obtain a definition for zeta of s, which is actually valid for all s with real part not greater than 1, but greater than 0. And importantly, this new definition for zeta of s agrees with our older definition of the zeta function wherever you have a complex number whose real part is greater than positive 1, but it extends the definition of the zeta function now to new values where the real part of s can actually be greater than 0. Graphically, this means that under this new definition of the zeta function has a valid meaning for all complex numbers in the right half plane, complex numbers with real part greater than 0, with the exception of the value s equals 1, where we have a pole. So by redefining the zeta function in terms of the eta function, namely by deriving the identity zeta of s equals eta of s over 1 minus 2 to the 1 minus s, we've extended or continued the zeta function into a new, larger domain in which it previously did not have a valid definition. So in this sense, the eta function gives us what's known as an analytic continuation of the zeta function. Again, this definition of the zeta function agrees with all of the original values of the zeta function that we found, where s has a real part greater than positive 1. But this definition also works for complex numbers with real part greater than 0. And furthermore, this definition shows explicitly that we have a pole of the zeta function at s equals 1. Now, the very great mathematician Bernard Riemann, who we'll talk a lot about later on, actually found an analytic continuation for the zeta function to the entire complex plane, but that's a matter for another day. Well, thank you for watching this video, and if you enjoyed it, please like or subscribe to my channel. Thanks again.